Hey everyone, welcome to another video. So in this video, we'll be looking at uh, the set of complex numbers and the basic operations of complex numbers. So let's get started. So the definition of a complex number is the following. So the complex number Z is defined as A plus BI, okay? Where I is equal to the square root of -1. So that means I squared is equal to -1, right? I squared is equal to -1. So make sure that you write that down. Next, we're going to look at the components of this complex number Z, okay? Complex number Z here. This quantity, this is read as the real component of Z. So it's the real number of Z. So the number that is not multiplied by I, okay? So in this case, the real part of Z is equal to A, okay? There's also this quantity, IMZ. This is read as the imaginary component of Z. Okay, that's how you read that. And it equals to the number that's multiplied by I. So in this case, it's B. Okay, let me write that out a little bit more clearly. B. All right. So A is what's called the real component of Z, and B is equal to the imaginary component of Z. So spoilers in the next section, we can represent complex numbers as a vector, okay, in what's called the complex plane. And here is what the complex plane looks like. So you'll have two axes, but this time, instead of writing out the x and y axis, we're going to be denoting axes as the following. So the axis will be called the x-axis. That will be called the real axis, the real part of Z, okay? The axis where we know as the y-axis, this will be called the imaginary axis of Z, okay? So if I want to plot Z equals A plus BI, for example, and without loss of generality, we're going to say that Z belongs in the first quadrant being here, okay? We can write out Z as a vector. Z is equal to this in vector notation, AB. So let's say this point is over here, okay? So this is the complex number AB in vector notation, okay? So with vectors, by definition, a vector has a magnitude and a direction. Okay, the magnitude being, let's say, R, and then the direction is an angle, let's say theta. And those are indicated as follows. So the magnitude is the length of this vector, R, And the angle, the direction, is going to go with respect to the positive real axis. Okay. So this is an illustration geometrically in how we can represent complex numbers, right, in what's called the complex plane. We'll go over more about this in detail in the next section. But this section in particular is looking at different operations on complex numbers. Let's go over those now. Operations of complex numbers. Okay, operations on complex numbers. Let Z1 equal to A plus BI and Z2 is equal to C plus DI be complex numbers. Okay. So this is the first property of complex numbers. Z1 and Z2 are equal if A equals C and B equals D. All right, straightforward. Okay. So two complex numbers are equal if the real components and the respective real components of Z1 and Z2 and the respective imaginary components of Z1 and Z2 are the same. A equals C and then B equals D. Okay. Also with addition, and this works the same way as subtraction as well. So it's similar to what you've seen in algebra, right? We combine like terms. Okay, so if I have Z1 plus Z2, right? A plus BI plus C plus DI. Well, this equals to the real components added together plus the imaginary components added together times I. So this equals to A plus C plus B plus DI. Okay, B plus DI. And the same goes with subtraction. Z1 minus Z2, A plus BI minus C plus DI. And this will equal to A minus C plus B minus D times I. Okay. So that's addition and subtraction. But multiplication is going to be different. Okay. So it's similar to what you have seen with rationalizing a denominator or numerator in some cases. If either one of those quantities contain a square root of a number, right? You multiplied and divided by the complex, by the conjugate, right? We'll go over complex conjugate soon, but let's talk about multiplication. Multiplication of complex numbers. Okay, so Z1 times Z2. Let me actually note this like Z1 times Z2, like that. So this equals to A plus BI times C plus DI. Okay, so we're going to use the FOIL method for this guy, right? So just use the FOIL method in algebra. So this will equal to A times C, right? Plus the outside terms, plus A times DI, right? Plus the product of the inside terms. So that would be plus, so that would be plus BCI, okay? And then multiply the last terms, okay? Plus BDI squared. So that would be plus BDI squared. But we know that I squared is -1. That's what the definition of I is. I squared is -1, right? So that means we can group all of the real components and the imaginary components of this product. And you'll have A times C plus, or minus, I should say, minus B times D. That's the real component, plus I times AD plus BC. So that's how you multiply two complex numbers. Now, before I get into division, I need to refer to what's called the complex conjugate. The complex conjugate. Okay. So this is the definition of the complex conjugate. The complex conjugate of Z equals to A plus BI is, we denote the complex conjugate as Z bar, and that equals to A minus BI. So really, the complex conjugate is you're switching the sign in the middle. Okay, switching the sign in the middle. That's it. Okay. So as an example, the complex conjugate of Z equals 3 plus 2I is Z bar equals to 3 minus 2I. Okay. And also, if I have Z is equal to I, right? The complex conjugate is Z bar equals minus I. Okay. And there's an exercise if, and it's kind of not hard to think about this. What would be the numbers in which Z is equal to its conjugate? What do those numbers look like? Okay. So I want you to think about this on your own. Okay. All right. So try not to think too hard about that one. Okay. The last operation I want to talk about is division of complex numbers. Division of complex numbers. So if Z1 is A plus BI, and then Z2 is equal to C plus DI, okay, C plus DI, then Z1 divided by Z2, okay, right? So A plus BI divided by C plus DI. Well, what we are going to do here with complex division is we are going to multiply and divide by the complex conjugate of the denominator. Okay, so it'll look like this. All right, so here is A plus BI over here and C plus DI down here. And then we're going to multiply each of these quantities by the complex conjugate in the denominator. Okay? All right. And so what really is going to happen here is in the bottom, you'll have C squared minus CDI plus C DI minus DI squared. Okay. And then you'll have the top as AC plus BD minus I times AD minus BC. Okay. All right. So, okay. So C plus DI Okay. Yes. And so what happens in the denominator is that these middle terms will cancel. They're the same. So that's 0. And this would give us AC plus BD minus I times AD minus BC over C squared plus D squared, since I squared is -1. Okay. So that is the division rule for two complex numbers. Okay. And these are the various operations on complex numbers. Okay. So hopefully that made sense. Let's go over some examples. Let's first evaluate the following. Let's see, I have them over here. Okay. I to the 8th, and then part B is I to the 11th. Okay. So since I squared is equal to -1, I squared is equal to -1, well, we're going to use some modular arithmetic to figure out what these quantities would equal to, right? Um, so, okay. So you want to think about a clock. It goes like this. So we'll have I to the 0, that's 1. I to the first, that's I squared, and then I cubed. All right. So you want to think about these problems as a clock. Okay. So what we do here is we divide the exponent on I by 4, and we look at its remainder. Okay. So if our remainder is a 0, the component is 1, right? Any number raised to 0 power is 1. This will be just I. I squared is -1, and I cubed is minus I, right? But if it's I to the 4th is just I times I squared times I squared. So those are both -1, but that equals to +1. Okay. So I to the 0 would have the same output as I to the 4th, and then I to the 8th, and then I to the uh, 12th, and then I to the 16th, and whatnot. Okay. So, yeah. So what we do is we take a look at the exponent number, we divide it by 4, and we look at its remainder, right? 4, 4 goes into 8 2 times, so the remainder is 0. Okay. So since our remainder is 0, I to the 8th is equal to 1. Okay. You can try this example on your own just as easily. Okay, so pause the video and try to work on that for a few seconds. Okay, so I assume you looked at it. So what we do is we take the exponent number and we divide it by 4. Okay, so 4 goes to 11 2 times, so that's 8. 11 minus 8 is 3. Yeah, that's right. 3. So since our remainder is 3, I to the 11th is equal to minus I. Minus I. Okay. So that's pretty straightforward. And here's this other examples for you to work with. Right. as in a plus bi form. Okay, so A, B, C. So here's the first one, 3 times 4 minus I minus 3 times 5 plus 2I. The second one is 2 minus 4I divided by 3 plus 5I. C is I times 1 plus I times 2 minus I times 2 plus 6I. All right, so these are some examples for you to work with. Pause the video and try to work on these on your own. And then I'll show you the solutions once you're done. Okay, hopefully you did all these examples. So let's look at how you would solve these, okay? So in part A, what we do is just first multiplication, do order of operations, right? So the first component would be 12 minus 3I minus 3 times 5, and then minus 3 times 2I, right? So it'll be minus 15 minus 6I, okay? Then just combine like terms. 12 minus 15, that's negative 3. And then minus 3I minus 6I, that's a minus 9I. Minus 3 minus 9I, okay? Part B, we're going to use division. So 2 minus 4I divided by 3 plus 5I. What we have to do here is multiply the numerator and the denominator by the complex conjugate of the denominator. 3 minus 5I, and then 3 minus 5I here. Okay? And so this equals to so this equals to so we'll have 2 times 3, that's 6, minus 10I, minus 12I, minus 20. Okay, so this is 9 minus 25I squared, so that's plus 25. All right, cool. So that equals to minus 14 minus 22I divided by 34. So this equals to minus 14 34ths minus 22 34ths times I. Okay. Hopefully that works. Hopefully you made sense of that. Let's see. Part C. Part C. So we had I times 1 plus I times 2 minus I times 2 plus 6I, right? Okay. So what I like to do is go from left to right. So from the left, we can multiply I by distributing it that quantity to the 1 plus I term, right? And so I'll have I minus 1, and then 2 minus I, and then times 2 plus 6I, okay? Next, we're going to use the FOIL method to multiply 1 minus I, and then times 2 minus I, right? So that would equal to 2I, so that's minus I squared, so that's plus 1, minus 2, and plus I. And then we'll have times 2 plus 6I left over. So that will reduce down to so that will reduce down to minus 1 plus 3i. And then we do multiplication one more time. So the first terms will be minus 2. The outside terms will be minus 6i. And plus 6i. Plus 6i. And, oops, forgot one more term. Plus 18i squared. So that's minus 18. Right? Minus 18. And that will be minus 20. Okay, minus 20. So hopefully you made sense of that too. Okay, so that's just pretty basic. So to check comprehension, I want you to work on these problems in the textbook. So in the last video. So comprehension check. So page 7 in the textbook, 10, 16, 21, 27, 37, and 45. Okay. So check out those problems and work on them for comprehension. If you have questions, please let me know in the comments. And in the next video, I'll look at the polar representation of complex numbers and looking at the complex plane in particular, right? So I'll revisit that again. But in the meantime, I will see you all in the next video. Thanks for watching.